G'day! Welcome back to Worms Maths Academy. Today I'll be doing this video in my psycho voice. Just kidding. Okay, welcome back. This is part 2 of exam 2019, exam 2 methods. We are about to smash it out. I didn't do it last night because I had a cracking headache from painting. So I thought I would do it now. Now this is early on Friday morning. All reports are that it's not too bad an exam, but I guess we're about to find out. Okay, so we've got our first function, x squared e to the negative x squared. X squared times, I always like to put negatives in, e to the negative x squared, interactive define. So we've defined the function, find f dash of x. So we want to find d dx of f of x. Simplify. Negative 2x negative 2x x squared minus, oh, I forgot the x. Oh, you stupid thing. X squared minus 1, that was the difference of two squares, e to the negative x squared. State the nature of the stationary point on the graph of f at the origin. So if I want to work out the nature, we can just double diff it and sub in 0. Given x equals 0. If it's greater than 0, it's a minimum. If it's 0, it's a point of inflection. If it's less than 0, it's a maximum. So we can say f double dash of 0 equals 2. Therefore, it's a minimum. Find the maximum value of the function, the values of x which the maximum occurs. So this is just pumping stuff into the calc at the moment. I'm pretty sure this is what the whole exam 2 is going to be like. Damn it, I'll just write it. So we want interactive calculation max f max. Okay, the max value is 1 on e. One on e when x equals, was it negative 1 on 1? Find the values of d for which that is always negative. Okay, so we want the whole function to always be negative. So if our maximum value is 1 on e, then d must be less than negative 1 on e. So let's try. Graph f of x. Let's zoom in. And then if I said negative 1 divided by e to the 1. Okay, and then if we say, make it smaller again. Yeah. So less than negative 1 on e, if it equals negative 1 on e, we're going to have intersection points, but we don't want it. We want it to be negative, so we can't include the turning points on the axis. Find the equation of the tangent at negative 1. So f of x, interactive calculation line, tan line, was it negative 1 or 1? Negative 1. Y equals 1 on e. So it's just a horizontal line. Find the area enclosed by the graph of f, the tangent to the graph at x equals negative 1, to 4 decimal places. So let's have a look. That 1 divided by e to the 1. So we want in between here and here to 4 decimal places. I don't think you can do it in here. Intersection, enter, enter. Dx intersection, there, there. So 0.0356, that's 0.357. So we want the integral of -1 to 1, 1 on e minus f of x dx to 4 decimal places. 0.03568. Hang on. 0.3568. That doesn't sound right. 3568. Did I check the next number? Yep. Okay, so that looks correct to me. Sometimes there's rounding errors in the graphing program, so let's just check it. So -1 to 1, 1 divided by e to the 1, minus f of x dx. That looks exactly right. Okay, off to a pretty good start. Find the minimum distance between the point M. So Mn be a point on the graph of f where m is between 0 and 1. So m, we would have m, what's our function again? M squared e to the negative m squared. That's right, isn't it? And our other point is 0e, so our distance, m squared e to the negative m squared minus e squared plus m minus 0 squared. Find the minimum distance and the value of m which this occurs, correct at 3 decimal places. Okay, so we want that, and then f of x minus, was the other point e, 0e, bloody hell, 0e, so e to the 1 squared plus x squared. We want to find when that's a min, f min, between 0 and 1. Okay, x equals 0.783, 2.511. So dd dx m equals 0. Therefore, m equals 0.0. So d equals 2.511. Min distance equals 2.511 when m equals, was it 0.783? Three decimal places. Oh, nice. Next question. 3x, x minus 30 squared on 2000. 3x, x minus 30 squared on 2000. Interactive define. Now what I always like to do with these is check between 0 and 30. We go from 0 to 30 and up to 10. So let's go out into our graphing program. 0 to 30, 0 to 10. Now you can see if you've stuffed it up because it should look the same, which it does. Find dy dx. Okay, so first one, we don't really have to do anything, do we? It's all calculator. Click simplify. 9 x minus 10 x minus 30 on 2000. dy dx is 9 x minus 10 x minus 30 on 2000, and that makes sense. There's a stationary point there, and there's also a stationary point there. So that set of values for which the gradient of the hill. So the gradient of the hill is strictly decreasing. So I'm just going to define that as G for gradient. So go in here. Okay, zoom auto. So when is it strictly decreasing? Well, it starts at 0, min of this graph, 0 to 20. So is it Tx? X is an element of 0 to 20 because we include, so it's saying the gradient of the hill is strictly decreasing, so I've got to look at the gradient of the hill and see when that function is strictly decreasing. The cable for the zip line, what zip line? Does it say that there's a zip line? Okay, here's what Parker's planning. I missed that one. Is connected to a pole at the origin at a height of 10 meters, 0, 10. And A is straight for 0 to A, so from 0 to some value A, it's straight, where A is between 10 and 20, so it's got to join somewhere here and here. The straight section joins the curve at AB. The cable is then exactly 3 meters vertically from the hill all the way down to the end. So this function will follow the same function here, but it's going to be 3 higher. State the rule in terms of x, the height of the cable from 0. Okay, so it's just, do we call it whatever we want? Okay, I'm going to call it h of x. H of x is f of, is it y? Y plus 3. Oh, alright, I'll write the bloody equation. 3x x minus 30 squared on 2000 plus 3 x is an element of a to 30. So let's define that. Why not? Plus 3. Define h of x. So if we go in and sketch h of x, that looks pretty good to me. Does it simplify nicely in the calculator? So let's type h of x. Simplify? Not really. Factor? No. Okay. Find the values of x which the gradient of the cable is equal to the average gradient of the hill for 10 to 30. Okay. Average m for 10 to 30. So f of 30 minus f of 10 on 20. So it should be negative f of 30 minus f of 10 on 20. So negative 3 on 10. Which the gradient of the cable, okay, so then we want to say, What's our gradient again? So 9x minus 10, x minus 30. On 2000 is equal to negative 3 on 10. So I'm assuming this works out nicely. That, copy, paste, equals that. Interactive advanced solve. Okay, find the values. So there's multiple values of x. So x equals 20 plus or minus, or 60 plus or minus 10 root 3 on 3. 60 plus or minus 10 root 3 on 3. So that means if we drew a tangent at those points, we can just check and make sure they're in that domain. 14, 25, so they're fine. The gradients of the straight and curved sections of the cable approach the same value at x equals a, so there is a continuous. State the gradient of the cable at a in terms of a. That's a weird one. 9, a minus 10, a minus 30 on 2000, was it? Find the coordinates of A with each value correct to 2 decimal places. So we've got the gradient at this point, but we've also got to get the gradient of this. So we've got the point A is A, and then I've got, what's the original function? 30A. Is it 30A? Bloody hell. F of, let's say A. Three A, A minus 30 squared on 2000. And then the other point is 0, 10. So I can find the gradient. What's that point? We're going to call it anything. We'll call it y. Therefore, the m of ay is 10 minus that over y2 minus 1, 0 minus a. Okay, so 3a cubed minus 180a plus, was it 2,700? 2,700a, and then minus 20,000, all one, wrong cas, 2,000a, and that has to equal 9a minus 10, a minus 30 on 2000. Therefore, find the coordinates of a. So we let that equal Didn't I have that somewhere recently? Copy, paste, and we sub A for that, and A for that. Edit, select all, solve numerically. Now A had to be between, was it 10 and 20? Bloody hell. Oh. Cut, edit, clear all. I think I didn't put edit, select, interactive, calculate, advanced, solve numerically, but solve for A. Okay, so is that right? It's between 10 and 20. I didn't put it in this time. .81. So that means if I sub given A equals 14.81, negative 3.29, and then if we do the same here, that seems to be right, I think. 14.81. Have I stuffed anything up? 3A, A minus 30 squared on 2000. So let's clear it all again just to check. So we've got f of A, f of A, that is my y value, minus 10 over A minus 0. So that's my gradient, and that equals d dx of f of x given x equals A. Select all, interactive, advanced, solve. Edit, select all, interactive, advanced, solve for A between 10 and 20. So A equals 14.81. So if A equals 14.81, that would, oh, hang on a sec. That's not the right function. I'm using F, but I've got to use H. Where the hell is H? Something's not right. Just didn't feel right. Okay, so what I'm saying is I've stuffed up because I used f of x, and f of x is my graph, which is down here, so I'm joining these two functions together. But I want to join the functions. Okay, so the gradient, we're going to call it ay. So a is a, and then was it 3a squared? A minus 30 squared on 2000 plus 3. We'll call our y-intercept 0, 10. Okay, so that's, like, to be define it, that in our case is h of a minus 10 over a minus 0. Okay, now that sounds better. So we defined it, clear. So h of a, they're notorious for doing this stuff in spec, minus 10 over a. Okay, now that equals 3a minus 30 squared on 2000. Is that plus 7, was it? Minus 10. Minus 7 it's going to be. On a. That equals d dx of, it's the same gradient, but we'll just do h of a anyway. Given x equals a. Select all, solve for a between, was it 10 and 20? 11.12. How call it to a? Given 10 is less than a, which is less than 20. A equals 11.12. And then we've got to find h of that. So h of 8.95. Did they call it B? So A is 11.12, 8.95. So hopefully that's right. Find the gradient, find the value of the gradient at A. So we want to find h dash of A. So d dx of h of x given x equals that value, negative 0.0948, m is equal to negative 0.1, because it's to one decimal place, so once you round it, that's what you get. Okay, That one's done. Woohoo. Let's clear all this crap. Clear all this crap. Clear all that. Okay, during a telephone call, phone uses dual frequency signal to communicate the strength of the signal given by that, where t is a measure of time. T is greater than 0. Part of the graph is below. State the period of the function. Well, it's 12. You can see it takes 12, is it? Seconds. Awesome, it doesn't say. Find the values of t, where f of t equals 0 for 0 to 6. 0 for 6. It's kind of stupid. Find the maximum strength. Okay, sine pi t on 3 plus sine pi t on 6. Sine pi x on 3 plus 6. Define. F max. F of x from 0 to 12. So what's the question asking for? Find the maximum strength. Strength. Where are we? So 1.760. 1.76. Doesn't have any units. Find the area between the graph of f and the horizontal axis for 0 to 6. 0 to 6 mod, because it'll make this positive, f of x dx, f of t dt. Okay. F of t the mod of um, 0 to 6 dx. Why aren't you working? Oh, it is. Okay, that's not seeming to work. It's going to be easier just to go from 0 to 4. So 0 to 4, f of t dt plus 4 to 6, so 6 to 4 to make it positive, f of t dt. Okay, so 0 to 4, f of x dx plus 4 to 6. On pi square units. Okay, let sorry, someone's ringing my phone as well. Is that right? I haven't stuffed anything up. 4 to 6. Ah, you dumbass. 6 to 4. 15 on pi. Okay. Next one. Okay, let g be the function obtained by applying the transformation t, where that's that. A, B, C, D are real numbers. Find the values of A, B, and C given that 2 to 0 has the same area calculated in part D. Okay, so 2 to 0, that area there is becoming that area there, and that area there is becoming that area there. So it's reflected in the y-axis, and then translated 6 units to the right. So A will equal -1. B won't have changed. B will equal 1. C, 6 units to the right. D hasn't been moved up or down. So C is 6. But you could move it any number of ways. So, like if I move it 6 to the right, then I could also move another 12, and I'd get the same thing. I don't know whether they're going to want this in methods. Plus 12n, n is an element of z. So you could have any factor of 6 plus 12 because the graph has got a period of 12, so you can move it left and right exactly that amount. The rectangle bounded by the line y equals k, the horizontal axis, the line x equals 0 and 12, has the same area between the graph of that, and the horizontal axis for one period of dual turning frequency. Find the value of k. Okay, so they're saying this area here, there's some value here that will have the same area. So let's say 12 times, it's got to be k, is equal to whatever that area is, which we just found. Was it 14 on pi? 15 on pi. Jesus, I'm having a bad morning. 15 on pi. Okay, so double that. Total area is 15 on pi. Now, if we know k is the same height, it's got a width of 12. I am having a bad morning. 12k. 12k has to equal 30 on pi. So if 12k equals 30 on pi, 12x equals 30 divided by pi. X has to equal, yes, I should just 5 on 2 pi. K equals 5 on 2 pi. So that will give us the same area. Okay, 4 on 625. Let's get rid of everything. 4 on 625. 5x cubed minus x to the 4. 5x cubed minus x to the power of 4. That was an x to the power of 4. Define it as f of x. Find the mean. Okay, so the mean is 0 to 5, x times f of x dx. So hopefully this comes up with a nice number because it doesn't see any decimal places. 0 to 5, x times 10 on 3, that is a nice number. Yeah, it is f of x. In a sample of 80 Lorenzs, how many butterflies are expected to live longer than 2 weeks? So that's 80 times 2 to 5 f of x dx. Times 80. 2. 4, 5, 6, 4, 8 on 624. 73.03. What is probably that a Lorenzs birdfly lives for at least 4 weeks, given that it lives for at least 2 weeks? So, so we went from 4 to 5, f of x dx, on 2 to 5, f of x dx, which is, get that, 4, .0288 .2878. Okay. I think that's right. The wingspans of Lorenzs birdwing butterflies in town A are normally distributed with a mean of, so let's say, n 14.1, 2.1 squared. Finally, probably between 16 and 18. So interactive distribution continuous norm CDF. What was it? 14 and 16 and 18. That was 2.1 and 14.1. So the probability, the 16 is less than is that right? Is less than L, which is less than 18. What did I say? 4 decimal places. 0.51512. Okay, it's considered to be very small. Its wingspan is as small as 5%. Find the greatest possible wingspan. Okay, so we want to do inverse norm. Left 0.05, 2.1, 14.1, 10.6458, 10.646 centimeters. Is it centimeters? Okay, yep. Each year, a detailed study is conducted of a random sample of 36 Lorenz butterfly wings. This can be very large if its wingspan is greater than that. Probably a wingspan at town A is greater than. Okay, so find the probability that 3 or more butterflies in town. Okay, so this is binomially distributed. We'll call it, say, B for big. Binomially 36, 0.05, 27. Find the probability that 3 or more butterflies. So the probability that B is greater than or equal to 3 is distribution discrete 3, 36, 36, 0.0527, 0.2947. How many decimal places was it? 0.2947. I think that is about right. Okay, the probability that n or more butterflies in a random sample of 36 and 10 are very allowed is less than. So the probability that B is greater than or equal to n is less than 0.01. Therefore, n is equal to. So we want to go from binomial. Want to go from x to 36. We've got 36 trials and 0.0527. Put that in a table of values. Okay, when is it first below 1? N is 7. For a random sample of 36 butterfly wings, p hat is a random variable that represents a. This question goes for a while. That represents a proportion of butterflies of very large. Find the expected around standard deviation of p correct to 4 decimal places. So our expected value is just the population proportion, which is 0.0527, and our standard deviation is p1 minus p on n. Oh, stuff it, let's just write it down. So the square root of that times 1 minus that on 36, 0.0372. What's the probability of some proportion of butterflies that are very large within one standard deviation as correct at 4 decimal places? Do not use a normal approximation. So 0.0527 minus 1 square root 0.0372, 0.0527, I should say, is less than p hat, which is less than 0.0527 plus 0.0372, which is, so that minus that, 0.01546. So the same thing, but this time a plus 0.0899. We have another decimal place, 4, which to convert it to x values, we times them by the sample size, which is 36. So 0.56 which is less than, was it 3 point something? 237824, which is 1 is less than or equal to x, which is less than or equal to 3. These were probabilities, which is equal to 1 to 3 binom CDF. Select edit copy. One to 3.73796. 0.7379, 0.7380 to 4 decimal places. The Lorenz birdwing butterfly lives in town B. In a particular sample, the approximate 95% confidence interval butterflies is calculated. Determine the sample size used. So 95% confidence interval. Okay, 0.234, 0.866, 0.234 plus 0.866, 0.234, 0.866 divided by 2. So that's our p hat. So our margin of error is 0.866 minus that. .0316. So the square root of 0.055, 1 minus 0.055 over 36 is equal to 0.0316. Was that right? Okay, so that's 1.96 times it. So that's our 1.5. Okay, so let's first do inverse norm, and we'll say 0.2025. So that's our value. We just want this times the square root, 0.055 times 1 minus 0.055 on x is equal to this. Select all, interactive advanced, solve, 199.94. That's not that. N, so therefore n is equal 199.94. Therefore m equals 200. Okay, last question. Thank God. Okay, f of x is 1 minus x cubed. The tangent of the graph at x equals a between 0 and 1. Yep, intersects the graph. The shaded region shown in the diagram below are this. Find the equation. Okay, so let's get rid of everything that's in our CAS. let's sketch the graph. 1 minus x cubed. However, I should define it out here. 1 minus x cubed. Define it as f of x. We want the equation of the tangent at A. Tan line f of x at the point A. Okay, 2a cubed minus 3a squared x plus 1. 2a cubed minus 3a squared x plus 1. Find the x-coordinate of Q in terms of A. So that's our x-intercept. So we let y equal 0. Solve for x. Combine 2a cubed plus 1 on 3a squared. 2a cubed plus 1 on 3a squared. The coordinate of P in terms of A. So where does that tangent intersect f of x? Negative 2a and A. So P, we'll say 2a cubed minus 3a squared x plus 1 equals f of x. Therefore, P is negative 2a. And then we can just say f of negative 2a, because that'll give us our y value. 8a cubed plus 1. Okay. Let A be a function that determines the total area of the shaded region. Find the area of A. So we want that area minus that area. Okay, so we know that is 8a cubed plus 1. This length here is that x-intercept, 2a cubed plus 1 on 3a squared, minus that negative 2a. Okay, so we can say the area is 1/2 2a cubed plus 1 on 3a squared, 2a cubed plus 1 on 3a squared, minus negative 2a, which is just plus 2a, times the height, which is 8a cubed plus 1. So that's the large area. And then minus from negative 2a up until 1 of f of x dx. Now let's make sure we don't stuff this up in the calculator. So 1/2 times bracket that value plus 2a times 8a cubed plus 1 minus the integral from negative 2a to 1 of f of x dx. That looks nasty, but let's combine it. 80a to the 6 8a cubed, 9a squared, and then plus minus 9a squared plus 2, all on 12a squared A for which it's a minimum. Now remember, A is between 0 and 1. So, interactive F-min, 0, 1. We want to solve for A. A is 10 to the negative 1/3. dA equals 0, therefore A equals 10. I don't know why that's worth 2 marks. It doesn't ask for the minimum itself. Consider the regions bound by the graph of F inverse, the tangent to the graph. Okay, find the V of B for which the total area of these regions is a minimum. Okay, so it's an inverse. So, let's sketch that graph. Sketch its inverse. So what do we know happens? We know f of A is f of 10 to the negative 1/3 is f of 9 on 10. Now, if it's an inverse, the area is going to be the same because they're both tangents. But because we swap x and y, then our A and B will swap. So if we have A and B as so if you've got a curve like this area, its inverse what area is that with? That one and that one. Like the x and the y values will switch. So if our x value that causes a minimum on the original graph is 10 to the negative 1/3, whatever its y value is, will be the minimum area for the inverse and the tangent at B, because they switch. Find the value of the acute angle between the tangent of the graph at F and the tangent of the graph of F inverse at x equals 1. So F at x equals 1 okay, so that, the gradient of that given x equals 1. So we know f dash of 1 is negative 3. F dash of 1 is negative 3. So we've got that gradient's -3. If I was to graph the inverse at 1, that's that's a vertical gradient, so that's undefined. So f inverse of 1 is undefined. So if you think about it, we've got f inverse is that, and then the other one we've got a gradient of -3. So that angle is 90. That angle there is, we know that tan, we'll call that alpha. Tan alpha is equal to -3. So alpha is equal to tan inverse of -3. So the area between them, and that's pi on 2, theta is equal to tan inverse of -3 minus pi on 2. I'm sure that'll be fine as an answer. We also know that, no, alpha is that. The angle between them, let's call that beta. Beta is equal to tan inverse of -3 minus pi on 2. What else could we say? Tan inverse of -3 is the same as that angle there, and that angle would be, or that's 90 minus that angle, or beta is equal to, by symmetry, that and that are the same, so whatever that angle is, the angle there is going to be the same. Oh, hang on. Tan inverse of -3 is going to give us that angle. Yeah, so tan inverse of -3 is going to give us this angle. So tan inverse of 3 would give us this angle. So if we did pi on 2 minus tan inverse of 3, because tan inverse of -3, oh no, tan inverse of -3 would give us this angle around here. So if we do that minus pi on 2, we get the area that's in the angle that's in between. Or we can say pi on 2, which is here, minus tan inverse of +3, which is this angle in here. Either of them are correct. So tan inverse of -3 minus pi on 2. Let's just check and make sure they're the same. Tan inverse -3 minus pi divided by 2. And that's because it's giving me the angle in the last quadrant. So I guess that's not correct, just because of the definition of tan inverse. So we'd go with this one. It'll be the same, but it'll be negative. So if I did that, and then minus that, that's our angle in between in radians. Depends on whether they're going to accept that tan, because in your cas, tan inverse is between -pi on 2 and pi on 2. So it depends on what VCAA is like. I mean, in methods, in spec you don't, if we get that other answer, so pi on 2 minus tan inverse of -3, if we change that, times it by pi divided by 180, well, times it by 180 over pi the other way around. The angle is not acute, so it's got to be the other one. So that's our answer. Okay, hopefully you understood most of this, and hopefully I didn't make any mistakes, but time will tell. Let's finish it up there. Hopefully you did well. If you're in the coming years, hopefully this helps you for your exams. Bye.